when we run the Leisen Reimer tree, Leisen Reimer binomial tree, and we execute, we debug here, we find that the values we get are very close to Black-Scholes. We would like, however, to verify that the results for the American call option would be close to true. With a European option, we know that when there's no dividend yield, the European option and the American option are economic equivalent, but we would still like to verify what is the value of the American call, and we would like to do that in a situation where we have dividends, so we must include dividends in the specification here. Now up to now we haven't added in that specification yet, so we would like to include a specification for dividend yield. The Q, double Q here didn't appear in the original volupta code, so I've put that in. I removed the double forward slashes, so it will now be read in and declared as a variable. But then I've got to toggle through the code here to make that consistent all the way through. So once I make that specification change, I must then come down to where else that would be important. So here we could put in Q, negative Q, for dividend yield for the D1 estimation, and for the D2 we also have to make that clear, so we can write negative Q again. Okay, and this is very much like the adjustment you would make for Black-Scholes as well. Also, we must change the specification we have here is R underscore N, and we've got to put in alter that for dividend yield. So what I might do is just copy that again, copy and paste, and I'll remove that specification and I'll change this to being, let's see, RQ. So I'll just put Q here, and the reason why I'm putting Q there is to denote that there's another that we have an R negative Q. So I'll open bracket again, R negative Q, and where else is that important? Well, we need to put it in here. So the Rn here affected U and D, which we'll use later for developing the tree. We'll just change this to RQ. Okay, so this is new, I suppose. Maybe I should write that. And Q. Okay, so I'll just make a little note. This is new. Okay, that the RQ didn't appear in the original volupta code. I've put it here. What's different? I'm making allowance for a dividend yield. Then otherwise, what happens? Well, that's read as U and D, and the tree is built in the usual way, same as a Cox-Ross-Rubinstein tree would be built, where the value of the stock in the tree goes up by U and down by D, and that keeps iterating for the number of steps in the tree. And we also, when we're discounting, well, we discount at the risk-free rate anyway, so that we don't include Q here in discounting back through the tree in this type of environment. Okay, so in addition then, what changes do I need to make so that the values here are consistent with the values that we observed in Broadie and Detemple 1996? So the stock price we're going to set at 80. The exercise is K is going to be 100. Risk-free rate 3%. Dividend yield is 7, and volatility is 20. Okay, so I'll take those values and put into our Visual Studio project. Okay, so keeping in mind Broadie and Detemple 1996, Table 1, the spot price 80, the exercise was 100, the time period was actually 6 months. The risk-free rate we said was 3%. The dividend yield we said was 7, so 0.07, and the volatility same as 20%. Okay, so let's run this again and see what happens. So I hit the debug, the program executes. I hope there's no errors, and I'll pull that. So in our debug window then we have this 0.21954. Okay, we can compare against our Excel results or the Broadie Detemple 1996 results, and we can see here for stock price of 80, 0.219, which is similar here, 0.219 for the American call. Notice that the American call and the European call vary in value in this instance because there's no dividend yield. If the dividend yield was the same, then we could, so if the dividend yield was 0 and we ran this, so execute, what we would find is that the value of the European call and the American call are the same, where dividend yield is 0. Okay, so let's, well, we could copy, edit, select all, edit, and copy, and go back into Excel for a moment and compare our results. So I'll just paste there, and you can see for 300 steps the American call 0. Okay, now dividend yield should be okay, so we should take this out, go back into our program. Dividend yield we said was 7%. Let's run that. Pull the results in, edit, select all, edit, copy, go back into Excel, and we'll paste the results, and you can see we're getting for American call 0.219. Okay, let's go for where the stock price is 100. So that just necessitates a very small change in the estimation. So to run that estimation then, we change 80 to 100, and we can run again and see what the effect is on the options. So the debug window has appeared. The values we get out are as follows: edit, select all, right click, edit, copy, go back into Excel and paste the values. And again here, for when the stock price was set as being 100, the value of the American call 4782, 4783, 4782. So approximately the same. Let's run again at a higher number of iterations. So we'll go back to, let's cancel this, go back into Visual Studio, increase the number of steps in our tree to 400, and run again. And we can pull back in our results, edit, copy, edit, select all, right click, edit, and copy, go back into the spreadsheet and paste our values again. So paste, and the value of the European call is 4782, 4783, so 47825. Okay, so there's a little bit, as we increase the number of steps, we are increasing towards 2, but Leisen Reimer is just here 400 steps, whereas here we take it that the number of steps is given as 15,000 for true. Okay, so the true valued column here is with 15,000 steps with a regular Cox-Ross-Rubinstein, with Leisen Reimer already with 400 steps. We have a reasonable level of accuracy. Let's go back and do one more estimation. This time we'll increase the number, the value to 120 here, and we will run again. So execute and debug, and the value we get here then for the American call, let's just check that for 1 second. It should have been, leave this as 100 in fact, and we're changing the stock price to be 120, and let's run that. Okay, and the debug window appears, and we're getting, okay, exactly 20. Let's edit, select all, right click, edit, copy, go back into our spreadsheet, and we have a value. Just copy where this is here, paste, and we now have a value equal to 20, which corresponds here. So when we change the stock price to 120, otherwise have the same values for the other parameters, we're getting 20 here. We're also getting 20 for these values. So if I reduce this to 300 and run, okay, so I'll have to debug again and run. So 300, okay, the value I get at 300 steps is 20, which is also consistent with the results reported by Broadie and Detemple for a 15,000 step tree. So overall, this would suggest that the Leisen Reimer tree is quite a good tree, and with a relatively small number of steps, the level of accuracy is quite high. The Leisen Reimer tree has produced results here that are relatively, well, quite consistent with the results reported by Broadie and Detemple. That would also suggest, perhaps, given the relatively high level of efficiency, Leisen Reimer could well be used to implement estimation of implied volatility for American call options. Okay, and that's something that's generally a little bit more computationally intensive. Implied volatility estimated for European option is relatively straightforward with bisection. For an American option, that's computationally intensive, and we'll see if we can implement a Leisen Reimer version of a bisection, and we'll try to determine how efficient that process is, and that we'll do in the next video clip.